guys are, you make your bets and you get your bags, the spades from home. That's the name of the game.
Turn this thing on. That's the problem. Is this tournament in person? Are we allowed to handle each other's cards?
Well, they haven't given me any grief about it yet, so.
Okay. Here's your tournament mandated rubber gloves. And you just, it's also a card throwing tournament. You literally get the card to the middle, which is where, and all players are just equidistant from one another.
Like our game. I think there's some coolest games that we have.
It is just very fascinating that we invented a standard deck of cards, humans invented a standard deck of cards, and everyone just comes up with something different to do with them. I appreciate that because it means you don't need to carry around 8 different types of games with you. As long as you have one standard deck of playing cards, you can make friends anywhere. In high school, senior year, I had a deck of cards in my backpack. Most other students, when they pulled out a deck of cards, it was friend-making time. Me, though, I was playing solitaire because I wanted something physically to do. I couldn't use my phone, and phones were dumber at the time, so there wasn't even much I could have done on it. So I just learned the game that I idly spent my time doing on a smartphone anyway. Most people were surprised that you could play it without a computer.
But in person, cards don't do a little thing where they get one by one. Like, that just makes
Yeah, the
sense.
best thing about on the computer is that when you win, you just like,
Yes, and then you don't have to clean it up afterwards.
Yeah.
Because you can still do that when you win in normal solitaire, except you have to throw the cards everywhere, and then you have to deal with the aftermath.
I'm not a big fan of 52 card pickup.
Not my favorite thing. I'd much rather just get to I would much rather get to another game of solitaire faster.
you know how to play chess?
Mostly,
I
it's
learned
something I
chess,
only do like once every
ago.
3 years.
Over Christmas break, that was my thing, teach myself chess.
You
Oh,
watched
okay.
that show, I don't know what show it's called.
Clean the gambit.
Sure.
I know the
Oh,
rules, but geez, is that game like 2 big grand to be there.
I was in college when I learned how to play checkers. Not
No.
because I didn't play checkers as a child, but because I'm the youngest of 5 and all of my siblings lied to me. I just learned that there's not a thing called a pickle jump in
Sorry,
checkers.
a what?
A pickle jump, which basically means you get to move your piece however you want. But if your opponent tries to do it, you say, no, that's not how it's done, and then they always lose.
So they were just making up some nonsense so that you, the youngest, would always lose?
Yes.
What the heck?
Sounds about right.
At least when my family made up rules for chess, everyone could use them.
No, they were only.
We used to
against
just
me.
play checkers with chess pieces.
Ah,
When I was little.
yeah, honestly, because I played a lot of checkers, but I didn't learn chess until I was high school and the youngest.
The game is,
What did it
the skill gap is unbelievable.
Oh, yeah. Like, if you're having a global tournament where everyone is making their moves
I've lived
in
through
like
20 years.
fractions of a second,
They used
I gotta take
Oh, you're the
like
oldest
15 minutes, I'm still like.
Yes.
I sit there on the
Yeah,
exact.
I was in my
eyelids while I was
sleeping
in the car. Like, they were mean to me.
I am way too
The
impatient.
one, I don't know if I would fall asleep, and Emily, who was the middle one.
My younger brother and I didn't know what all the differences
Sleep,
between the
she was
pieces
little,
were,
so
so
we
we
had
just
to
invented
call,
super
and I was
chess.
like,
Where
we didn't
literally,
want to start the car, so we were.
it was just one person coming up with something nonsense that their piece could do. And then the other person would do the same thing. I think my favorite was King Vision. The king just has laser eyes.
Okay. Now the game's interesting.
We also called her loser, and then we got in trouble for it.
Oh, yeah.
Flipped it
Speaking
and
of
called her
lasers, we were talking
wrestler.
about that last time.
Sorry?
And my dad thought that was funny.
Yes, I was talking about lasers
Yeah,
last class. But we
They
talked
were
about how the
mean to me,
sun
but
is
they
a
also
laser.
lied to me.
Because
I was
all
convinced
forms of
for years
radiation
that my sister
transfer
did.
energy from one place to another.
Like,
That can include thermal.
Why would you lie
In fact,
about that?
like
But
this,
I,
mostly
I
becomes
do it.
thermal.
I'm super proud.
I don't think it becomes any other forms of energy besides other radiation types.
They're my age, pretty much.
yeah.
Also, without the atmosphere, the sun would be a dead
They
giveaway.
look
at
like
1:30.
Why is my phone ringing? I'm at work, yeah, but I'm sorry.
I really like your bug, by the way. Thank you.
I haven't been back to my
Me, for you. Oh, you're traveling?
Looks fun.
No.
What was fun?
What?
Sorry. I assume everyone's talking to me at once and it becomes a problem in my ears. But then when they're not talking to me, then I just get embarrassed.
It happened.
What happened? Hey guys. It is Thursday, my dudes. So, we are going to pretty handily finish chapter 11 today. Might even begin looking at 12. Beginning of 12 is just the laws of thermodynamics, so that shouldn't take long. Just check something real quick. As far as finishing chapter 11 go, we're going to look at just a little bit more math for thermal conductivity. I forgot how to talk for a second there. It happens sometimes. And then we'll look at some various examples, combo examples from throughout chapter 11. Maybe look at a couple specific things from the homework in case I didn't mention something that is specific to that assignment. So, any other questions, comments, concerns, goofy side tangents, etc. before we begin? Okay. Sorry, additional brief reminder before we get too started. The chapter 11 assignments are currently due here. The chapter 12 assignments will be due here. That is also the day that our first test is presently scheduled to open up. We'll adjust that as needed. But as a reminder, it will open up on this day. That doesn't mean you have to take it that day. You will have until class on Thursday.
So it's on WebAssign, is that
Yes.
right? So we'll do it and then send you our work? like,
Correct.
you know?
Yes, always send me your work. Any WebAssign assignment, you can always send me your work.
When does
For the
it
test,
close?
it's required.
The 23rd will
The 25th. And as a general rule, just to make sure you guys have time to do everything during that week, I'm not going to have labs during test weeks.
Thanks.
So there's a lab this week, there's a lab next week, but this week, that has the chapter 12 homework due and the test, we're not on labs.
I mean, we can't get over that.
Well, it also means I'll catch up on my grading. That's the goal, at least. And, I mean, if we're moving to test outside of class, then you need more time outside of class to do with it, and the lab is the thing to cut. We have plenty of weeks to get through them all.
We're not upset. It's really exciting.
Okay. Thank you for this information. You set my mind at ease.
Wait, do we have class on the 23rd?
Class, yes.
Okay.
Lab, no.
Okay.
Class, yes. We will review everything from the 3 chapters we've covered, make sure everyone's set for the test that week. Pardon me. And then we will move on after that point, like well into, like after the end of that week, then we'll move on to the next core of the class. Now, to get there, we have to finish chapter 11. So, in our lecture and in our lab, we've been analyzing this formula, in this part down here, talking about thermal conduction, thermal power, those terms are basically synonyms for right now, and looking at the various things that affect that, and finding the thermal conductivity of the different objects. This is the standard metric version of the formula for single objects. You can plug in what that object's made of, its surface area and its length, and you can figure out the thermal conductivity through it. There's a different version of this formula that is more commonly used for most people in the United States because it's used in the construction industry. I mentioned this if you have lab already this week. I've already done this slide, so no. This version is how you look at multiple layers of something added together. For example, let's take a look at, you all probably have something similar, a thermos or insulated cup of some description. This particular vessel is likely not solid metal. Most of your insulated containers probably aren't solid metal. One of the reasons for that, you can keep, sorry, I'm just going to backtrack real quick. You can keep copying in a second. This is likely not solid metal because the metals have the higher thermal conductivities. The higher this number, the faster thermal energy is going to move through it. So if this was just solid metal, would it keep my water very cold? It would. That means that this is definitely some composition of multiple things. Odds are it's like one metal vessel with thin walls, and there's an air layer between that and the actual outside casing. That's probably what most of them are. But they may have other insulated materials in them as well. Point is, though, it's layers, like onions or ogres. The joke's still relevant?
Yes.
Okay, good. And the original version of the formula doesn't take layers into account. You could do each object one piece at a time, but that gets a little tedious. So some scientists figured out how to wrap every layer up into one formula. The version up top is the more metric-friendly version. We can use all the same numbers, units, and constants, like the previous constant table, with this version right here. To briefly explain the difference, let me just rewrite the way we had it before. Originally, the K was up top multiplied by the A. We still had the temperature difference, bless you, over L. Now, the K is on the underside of the denominator, and it has been lumped into this weird sigma term with the L. So, recall, when sigma is used in math, it means sum of, S-U-M of. So, what this term represents is all of the different layers added together in terms of their thickness and what they are made of. So, let's say, for example, well, let's look at that thermos real quick. Let's say that its three layers are, first, 1 millimeter of aluminum, then 3 millimeters of air, and 1 millimeter of, let's shake it up and say steel. Each of these layers has a different thickness and is made of a different material. And therefore, they would all have their own unique L over K value. If you take that length and divide it by the K of that material, they would all have a different fraction here. Each layer individually has its own specific L over K. And so sigma of all the L's over K's for each layer, or whatever, every layer of every material present in your composition. You just want to divide the thickness of that layer by what it's made of and add it with all the other LKs. So if we were going to keep examining my specific vessel here, let's backtrack just a second. See if my marker with more ink in it. So the K for aluminum is 238. The Gesundheit.
Thank you.
The K for air is 0.0234, and the K for steel, well, this doesn't actually have steel on it, so let's just use irons for the time being. And we now have these three fractions, and we find the number that they're all equal to, then we just add those numbers together, and that will be the sigma L over K. The sum of every L over K that is present. So we can still use this metric table and all the metric units of measure that we have been using, but that's apparently not good enough for the American construction industry, who really likes their imperial system. So, common U.S. workplace standard is, instead of measuring lengths and dividing by metric conductivity constants, the U.S. housing industry has created its own constant instead, bless you, of R value. And this, just looking at the difference between these two formulas, the only difference is that L over K has been replaced with R. So the R constant is L over K. It talks about the thickness of the material and what it's made of. So this table of R values, and you can tell we use it in American industry because it's feet per Fahrenheit. I don't know why we... Anyway, sorry. Each of these entries here is a commonly used material in U.S. construction, and they all come with a thickness in addition. So you've got specifically 1-inch thick hardwood siding, 4-inch thick brick, a couple different thicknesses of fiberglass. This table comes with the length prepackaged. So depending on which version of the question you get, you will have access to the table of either K's or R's. I'm going to prefer using this version for this particular type of question, because that is what often comes up in the book, and that is what is in the homework assignment. But that is where the R comes from. And since the R is L over K, sigma R is just the same thing. Add all the layers together. Same basic formula, just tweaked slightly. And it's useful because most things are combinations of layers, like the thermos or one's clothing. And it's interesting to see how they work together. Just looking at the three things we listed a second ago, which of these layers is going to do the most insulating work? The air. The air's constant is smallest, which means that this term is going to end up being, is going to add more into the total than the rest of them will. Honestly, you'd probably be just as fine if the air was the only thing insulating your material, but it's not air is not a very good cup.
So what about that weird aerogel stuff?
That is a very good insulator, just don't set it on fire.
What did you just ask about?
Aerogel?
I think marshmallows, but even less dense, and don't eat them.
Good to know. Sorry, all I heard of that was the don't set it on fire part, but I was concerned.
Well, don't set marshmallows on fire either. Then they might be for s'mores.
How are they supposed to be doing that?
I like my marshmallows burned.
Well, I'm just not very good with super hot food.
You let it
So-
cool, you catch it on fire, and you get it all black and burnt, and the inside is all gooey, and then you smush it in a form.
I mean, s'mores are disgusting to begin with, so.
When I was a kid, I didn't much care for them either because it was work to melt the marshmallow, and I would rather just eat the chocolate.
As long as it's not make kids,
Sorry,
Jeremiah, don't be sensitive.
I'm like 30.
I didn't like them when I was a kid. Period. Sorry. Slip of the tongue. Okay. Let's just use that imperial version really quickly. So to look at things in terms of the construction world, on the hottest day of the summer, well, might not be the hottest on record, but let's just say for the sake of this question, it's 110 degrees outside, Fahrenheit. And the walls of your house are made up of a composition of 4 inches of brick, 1 inch of fiberglass insulation, and then some drywall.
At my house,
Hmm?
at your house at the front.
I didn't hear you, sorry.
It says your house at the front, that is my house.
The hypothetical you in this timeline, this hypothetical alternate telling.
Is the drywall thickness not gonna?
It's written on that chart.
Yeah, the chart just specifies the one thickness of drywall, and so I forgot to write the half inch on the slide. But while we're here, let's go ahead and copy down all of the R's that we want. R for 1 inch of, wait, how much fiberglass was it?
1 inch.
1 inch, thank you. All right, that is our fiber equal to 4.5. On our brick. And it is specifically 4 inches of brick, so 4.00. And then our drywall, 0.45. So the drywall is definitely contributing the least to this.
Would we ever have a problem like 2 inches of brick and we would have to like move that and get the art out of it?
I have no intention of doing that, but it should just be cut in half if it did come to that. I would expect. Yeah, if it was half the thickness, you could just cut the number in half, but I'm going to try to keep it to the numbers on this chart. But if a homework question gives you something stray, usually it will either give you the number you need or try to make sure it's given to you elsewhere. Other pieces of information that we should know. Walls have a height of 10 feet and a width of 20 feet. Height and width aren't in this formula, but area is. So what's the surface area of your walls? Very good. This is technically feet squared. But that's fine, because the table gave us our R values in terms of feet squared and Fahrenheit. We were using that imperial table a second ago. So no need to panic convert this to meters. This is the one time feet in Fahrenheit will be commonly used in this class. And the temperature hot is 110 Fahrenheit. Temperature cold on the inside of the dwelling is 70 Fahrenheit. What is the rate of thermal energy transfer through the walls of the house? All right. So, we found our area. Delta T is, since it's functionally a delta T, and since this formula constants are designed to accept Fahrenheit, we can plug in the two Fahrenheit units here as long as they are both Fahrenheit. So, this is the one exception to our metric only policy. Then, for the sigma R, we're just going to add up the R's for all of our layers. That should be about 8.8, I think.
You got 909?
What would the units for power be? Very good. Did it right.
What if you told that?
Yep, 909. Oh, hold on a second. Ah. Okay, so it is worth noting that this constant is not in terms of joules. It's in terms of British thermal units per hour.
I hate the United States. I really do.
I certainly didn't make the rules. So instead of watts, watts is the metric joules per second, this would technically be BTU per hour. Which makes my second question a little bit moot.
Well, BTU is a cool thing, like a bunch of planets together.
Yeah, but why does Britain get their own thermal unit?
Why does the United States use the imperial system?
I don't know, especially since, like, the United States has been historically very anti, no, wait, I can't even say that.
Okay.
I was going for, we were very anti-British Empire, it's not to say we didn't start one of our own.
They can get hot in Britain, but
What's the difference between like the vertical airspace and the stagnant layer of air?
Ah. Oh. Vertical, I assume, will employ convection to some extent,
Okay.
but stagnant, if it's transferring horizontally through air, that's going to take a lot longer.
So like in like the water bottle, like that's like a U shape. It's inside a U shape. Yeah.
Yeah. So,
So
okay,
when it
there is
has
a little bit
both-
of vertical air down here, but it's mostly
It's mostly
horizontal
okay.
stagnant. And I'm not going to cut it open if you're going to find out. I would bet that there's probably styrofoam in there instead of just air, or just a little bit of structure. Although maybe just air based on how it sounds. Hmm?
it's like a door, you know.
You lighted it up for me.
So, this formula works real nice because it gives us the R's and you just add them up. The downside is the weird imperial units. Literally every single unit in the constant and the formula is different.
That's fun.
Yes, but it is the primary application for this specific principle in the United States, so it's worth mentioning. So, with that, that is all of the unique formulas and materials needed for Chapter 11. And I've been going on for a little bit now, so I say time for a quick break. I'm going to glance over all the homework questions and see if there's any unique cases that we should go ahead and talk about before you guys are set loose for the weekend. And you guys can take a quick brain and water break.
piece of material from chapter 11. So what I want to do is one more example, sort of it's a specific thing that I didn't show you because we sort of ended at a weird time during one particular lecture, but there's homework questions like it, so I'm just going to refer back to it in a second. First, this is something to have in your notes because there's at least one homework question that involves British thermal units. So, do have this conversion copied down. Additionally, the chapter 10 and 11 notes are on Brightspace. So I do advise you to have access to those while doing your homework because it has all of the tables of constants in them, just in case the question squirrels that information away somewhere, you just have it immediately at your fingertips. In general, though, since you asked, you mentioned it, and I do want to go ahead and cover it because it may come up on assignments. These R values factor the length in, and if, say, you were looking at 2 inches of brick instead of 4, you could just cut this in half. So, in general, whatever the fraction is compared to this, you can multiply that ratio by the number to adjust it to whatever the actual thickness of your material is. So, let's say that it's 1 point, sorry, let's pick. This vertical air has 1.01 for 3.5 inches. Well, let's say we wanted vertical air that was only 1 inch thick. I would recommend just cross multiplying and compare 1 to 3.5, like we would compare whatever the final R value we're looking for to 1.01. You can solve and find the adjustment value.
I have a question.
Yeah.
Can you explain the difference between specific heat and thermal conductivity?
Yes, they are connected. I'll put definitions up because, for the sake of anyone who benefits from reading things, specific heat refers to how much energy it takes to change something's temperature. So it refers to amount of energy needed to find the right age. So water has a very high specific heat because it holds a lot of thermal energy in it before its temperature changes. Other things with a high specific heat include metals. They heat up very fast. So it refers just to the temperature changing properties of that item. It doesn't necessarily say anything about the speed at which thermal energy will enter that item. Just how much it holds, or how much it needs in order to change temperature per unit mass. Meanwhile, thermal conductivity refers to the speed at which thermal energy travels through an object. My handwriting is deteriorating. I apologize. Bless you.
So
So specific heat is a Q and thermal conductivity is a lowercase k.
You are correct with lowercase k.
Okay.
Specific heat is C.
C, okay.
Q is heat. Q is thermal energy flow. Uppercase Q is. So, this specific heat cares only about temperature and not about speed. Thermal conductivity cares only about speed and passing through the one object and doesn't care anything really about what that object's temperature is. It just cares about the gradient of temperatures from one side to the other. So this is using the material as a bridge. This is talking about the temperature of the material itself. And they are connected. Most of the time, something with a high specific heat will probably have a high thermal conductivity, and something with a low specific heat will probably have a low thermal conductivity. With one exception, guess what, and shock of all shocks, the one exception I can think of off the top of my head is water. Because it's just an exception to every rule. Water has a high specific heat and a very low thermal conductivity. And that I don't have a very good answer for, actually. Just a noted irregularity. So they're connected, but not identical.
I'm just curious how you know when to use which one. Like, what it would be asking.
Okay, so specific heat and the formula that it is found in, where's my other marker? So, specific heat questions will tend to involve one object transferring thermal energy to another and trying to figure out what the final temperature of one of the objects in question in thermal contact will be. It doesn't usually specify how long this process takes. Two things are in thermal contact, thermal energy will transfer from one to the other, and knowing their mass and what they are made of, your goal is to find out what the final temperature will usually end up being. Or conversely, if you know the final temperature, maybe you want to solve for specific heat, figure out what the material is made of. These questions are usually about the temperatures. And those variables do come up in thermal conductivity questions, but if there's a question about thermal power, then it's going to be this version. Because this formula has nothing to do with time or speed. This formula only cares about what the temperature of an object will be when an amount of thermal energy is added to it or taken away from it. Yes?
Where is time in that cycle?
It's technically buried within the P, because this is the other formula for P is Q over T. So thermal conductivity is a rate. We're using one object as a bridge from one thing to another thing. So it will always describe what's happening on one side of one object versus a different side of one object. Meanwhile, specific heat questions, you're looking at the one object and you care about the thermal energy entering that specific object. It doesn't matter what side, it's just this is the amount of energy the object got, what will happen to it because of that. But at times it will also just come down to probably rereading the question about 3 to 5 times. I'm trying to make sure that the assignments are clear on what is specifically being asked for. And again, the standard procedure I always advise is write down everything you are given and write down what it asks you for and find the formulas that have those things in common. Using those methods should help keep them distinct, ideally. But they are definitely interconnected, so if there is some interconnectedness between them in your brain, it's not a problem because they are related. At times they're basically proportional to one another. But as an example of one type of question versus the other, this is a common specific heat question, so to help enforce what one looks like versus the other. I've been talking too much in the water already. So, just go ahead and say this is a specific heat question. So it's going to be MC delta T. And this is an actual process that most metallurgists will go through to identify what something is made of. It's one way of determining the things anyway. And for those who didn't know, metallurgist is, at least as far as my definition of it, scientists who study specifically the properties of metals. So, in this specific question, we have some object of unknown material. It's some lump of metal, but we don't know how much metal. I'm sorry, we know how much metal, we just don't know what it is. But we are told its mass. And we are told that the starting temperature of this particular piece of metal, so temperature, initial metal, is going to be 800 Kelvin. This scientist took the metal, heated it up to this temperature, and then dropped it in some water. And again, this comes up pretty often. You determine, based on what the final temperature of the water is, you can figure out how much thermal energy the water gained, which will tell us how much thermal energy the metal lost. We can use that to backwards determine what its specific heat is, and then compare it to this table to see what type of metals would have that specific heat. Which is handy for determining gray lumps of grayish metal, because what color is most metal? There are other more advanced ways of determining what things are these days, like mass spectrometry.
Yes.
Thank you. But those machines are big and clunky and expensive and not very portable, so this is what we did in the olden days. So, the metal's been superheated to very hot. It is dropped into 1 liter of water. So I'm going to specify this is mass of metal and mass of water. What would the mass of 1 liter of water be? Very good. Okay, that way. The water initial temperature is 25 degrees Celsius, and final temperature of both the water and the metal is 26.5 degrees Celsius. Since they're touching each other and they end in thermal equilibrium, they're going to end at the same temperature. We are asked, what is this metal most likely made of? We are going to determine that by finding its C value, its specific heat. what formulas do we care about right now?
Q gain equals Q lost.
Very good. One object is going to gain heat, all the other loses it. And I like to write Q gain equals negative Q lost to take care of the negative sign within the loss to equalize them.
Q
So-
equals MC delta T.
Very good. So, on the gain side, the water is going to gain some specific heat, and we know that Q equals MC delta T. So for the water, we have mass water, sea water, yes, which has a slightly different specific heat to normal water. So we have M water, sea water, and T water, which is different from sea water.
Not else when they go to the ocean, right? Just
Yes. And to this day, the Boston Harbor is still leafy. And meanwhile, as the water gains thermal energy, the metal will lose it. So the Q lost is we're looking at Q for metal will equal mass metal times C metal times delta T metal. So I'm going to go ahead and start plugging a few things in. We know the mass of our water is 1 kilogram. What's the metric specific heat of water?
4,000 something.
Yes, it is 4,000 something, 4,186. Is that up here? It is up there. And that's a known constant, so you'll always have access to it. Delta T for the water. The water ends here, it started here. So 26.5 minus 25.
Does that get to be in Kelvin or no?
Kelvin is always your best bet, but this is a delta T formula, so it doesn't have to be. Speaking of Kelvin, we're going to do the same thing on the other side, but weirdly, metal's initial temperatures in kelvins. Meanwhile, its final temperature is in Celsius, so something there has to change. Dealer's choice as to which one you convert. Because it's a delta T on both sides, this is a weird case where as long as both of these are Celsius and both of these are the same as each other, you can use either 2 kelvins or 2 Celsiuses here. So up to you which number you convert. So M negative times the mass of the metal, 100 grams. How many kilograms is that? 0.1. C of metal is what we are solving for. That's still empty. And then delta T for the metal. We know the final temperature in Celsius, so I'm inclined to keep the 26.5. So what is 800 Kelvin in Celsius?
527.
Very good. So there's going to be a little bit of distribution and multiplication and calculator foo, but we have everything we need to solve for C metal. must have wrote this question from a different table of specific heats because the answer's not on this table.
Is it 125? That's what I got.
That's what I got.
That is also what I got.
Well, maybe there's just some impurities.
Well, the two closest are lead and gold, and it said grayish.
Oh,
So
I
it's
didn't
like-
see lead up there for some reason. So yes, the two closest values, we have lead and mercury is pretty close. Where's gold? There. So our three closest numbers to 125 are gold, lead, and mercury. Process of elimination, if our metal is solid and gray, it's not liquid mercury or yellow gold. So this person just boiled lead.
Oh.
Couldn't that kind of, never mind. I was gonna say, you probably could have guessed that, like, without doing all of that.
Probably. There's other visual identifiers for lead, such as its mass and its texture, and ideally, some sort of a container saying, do not lick. But I hope no one is ingesting things that they find in their lab.
I mean, like, how many metals can just get up to 800 Kelvin? Just like, not know.
Well, probably not lead, actually. Lead has a very low melting point.
Yeah.
I don't know what it is, but I know it's on the low side. Lead is poisonous, brittle, has a freakishly low specific heat, and I lost my train of thought. Poisonous. It's poisonous, it's way too heavy, it's brittle, meaning you can't really bake anything out of it. It has a weird specific heat value, and it melts at a very low temperature. It's just a weird thing that has barely any uses, except apparently making paint brighter.
And fishing weights.
You use lead for that? That's terrible.
Yeah.
It just puts it in the water.
I've never known a fisherman that didn't put it in their mouth too.
Oh, you bite on it.
Yeah,
That's
that's
how
how
you
you-
close it on the
Yeah.
line.
They're all lead? They're all lead?
90% of
Yeah.
them. I put them in my mouth, that's probably not the best.
Where do they used to make gold metal?
What is it?
I
Like
need
a
to call my
fishing
dad.
It's like the weight that you clamp onto the line so that line sinks. It's like a little lead ball and you bite it onto the line.
Well, and our fishing industry is still alive, so, yeah, I guess not too dangerous.
This is my, okay, my dad has the good sense to pack pliers in his fishing bit. I don't think he bites them. That said, every time you cast out, you would be leaching lead into the water that the fish exist in, which probably isn't great.
I mean, he's fine right now, isn't
It's not mercury, so it's fine. It says that today other metals are replacing it.
Okay, good.
All those lead is still used. They're the older ones.
Look, I know we need to use it for something, just not anything involving water or organic life.
In some fishing areas, lead is banned, and
That
anglers
better
must
be.
use other sinkers.
Are they gonna go over and make sure it's not a flavors on it? Yeah, okay. Who's interested in that?
Not being hard.
Now they make them out of brass, steel, and bismuth.
Bismuth, yeah.
That's for the rich people that can afford the fancy weights. I now go to the Bass Pro Shop and get me some lead weights because they're half the price of the bougie weights.
Well, ideally, you only need but a few of them, and they're only gonna break off every so often.
Unless you're me, they break up all the time.
Oops, that does sound like my luck. I once got stuck on the bottom of the sea floor. I had a line stuck on the bottom of the sea floor.
Okay.
Okay. So that covers most of pretty much every type of question that you can expect to see on the assignments. And those are currently due next, 11 assignments, by the way, are due next Tuesday, the 16th. So after we're done here today, please continue working on this and come with any questions you have on
There's
that
only
day.
7.
Sorry?
There's 7 questions.
Yes, yes, there is.
You said 11.
Is that 11 questions? Oh, it's in chapter 11 assignment.
Oh, gotcha. That's my bad.
Now I'm thinking about 7-11. So, be working on those, come with questions, email me with questions as well. This is basically our version of Friday for this class, so I don't want to keep you, but I will at least go ahead and put something in front of you to put it in your brains as you are packing up.
Should we not pack up?
Huh?
Should we not pack up?
It's the end.
I mean,
Go
you
ahead
have
and
us
start.
for 10 minutes, so tell us now. for the
Okay,
culture
no.
piece.
Let's not start that.
No, you guys can start packing up. As we go ahead and lead into what we'll be doing next week, to put in your heads, we're going to start in
I
with
just
the
didn't want to
laws
be
of
like, just kidding, I figured
thermodynamics,
something out.
which are very important. They're up there with Newton's laws in terms of how important they are for us understanding the universe around us.
Yeah, they wouldn't let me take it at the technical college because they didn't cover thermodynamics.
Wait, what? Oh, man.
I was very mad.
That's completely valid. Who doesn't cover the laws of thermodynamics?
No, I learned a lot of thermodynamics in the middle school class, so I don't really understand why I had to learn it yet.
Well, I guarantee you've seen most, if not all of them before in other science classes, or at least referenced in other science media.
I think your heart loves.
The first law of thermodynamics comes up a lot, as does the second.
Issue with zero.
Yeah, it was added, I'm fairly confident the zeroth law was made after the core 3. But at that point, we were very married to the 3 laws of thermodynamics. Who wants to add a 4th? So instead, it's being treated as a supplementary intro statement.
Obviously.
It's just a commutative law of temperature. If A equals B, B equals C, then A equals C.
Happy weekend.
Have a good weekend. These will be up soon, so do please begin looking at them if you're done with the 11 stuff. All right.
Thanks for having me.
Awesome. Have a good weekend, everybody. Or a good lab day if I see you there.